So we're looking at doubling time and half-life of exponential functions. If I have the graph of an exponential function, so it could be y equals b to the x. It could be a multiple of b to the x. Still going to have the same shape because you could always relabel the graph of b to the x to represent a multiple of the graph of b to the x, kind of the way I just did with the logarithmic function. Okay, what do I mean by doubling time? Well, I can test whether I did a good job of sketching an exponential function here. And let's let the variable be t, since we're talking about time. Might as well make this a function of time. So here's t, and here's y. Okay, well, right here the value of the function is 1, or if it's a multiple of b to the x, ab to the x, that would be a. It doesn't matter. Okay, how far do I have to go here before the value doubles? Well, let's just take this value and double it and see how far I've got to go. Okay, that's how far I've got to go. Okay, so the function doubles. Doubles the y value. Now let's see if I want to double it again. Okay, well, here's the y value. I double it again. I'm here. Doesn't look like I did a very good exponential function. Okay? We call these doubling times. And I'm just going to represent the doubling times by arrows, because those arrows represent the times it takes to double. It took longer to do this doubling than it did to do this doubling. I didn't make that thing go up fast enough. Okay? I really thought I was going to do pretty well. Might have if I'd paid a little more attention. But I thought I knew how to draw an exponential function. My log functions have turned out pretty good. Okay, different doubling times. So I had a bad graph of the exponential function. If I want to make a better graph, I say, okay, let's see. The function doubled between here and here. So let's use that as our doubling time. And it's going to have to double again between here and here. So on this vertical line, the value is going to have to be twice as much as it was here. Because at the end of this doubling time, here was the value. Now I've got to get this value on this line, which means that my graph should have gone through here. It also means that if I go backwards the same distance, I should get half as much. Well, actually, I kind of did okay with that. That looks like it's about half as much as this. So I don't have room to draw that. It would be hard to see anyway. So that looks kind of okay. If I go back another doubling time, it should be half as high as it is here. Well, is this about half as high as this? Yeah, that's plausible. Looks like I was doing okay here and then I choked. Okay, that's all there is to it. So my graph would probably, stay along here. But it would have to go back up a lot faster. So That's a bad graph of an exponential function. This is a better graph. Well, let's look at it algebraically. First of all, what's the doubling time of y equals b to the t? Well, let t sub dub be the doubling time. Then b to the t plus t dub has to equal 2b to the t. Interconvertible. Okay? If by t plus t dub is t dub time later, and if that's a doubling time, that's got to give you twice what you got at t. Can we solve this equation? Well, it's easy to solve for t dub if you know the laws of exponents and use them with a little bit of experience and cleverness. I'll claim experience, I don't claim being clever. First of all, b to the t plus t dub by the laws of exponents is b to the t times b to the t dub. And if that's not totally obvious to you, and it usually isn't to people at this stage, but y'all are a pretty good class, maybe it is to everybody. If it isn't, you want to be sure that you understand this, okay? You know, it's a b to the a to the b plus c is the way it's usually written, is a to the b times a to the c. Familiar law of exponents, but people don't use them enough, those laws, to be really comfortable with them. Okay, at least usually. Well, anyhow, that's going to have to be equal to b to the t. Now, I could ask you if we had time to respond by chat and so forth and tell me how this simplifies, but I've got to just tell you, you divide both sides by b to the t, and this b to the t and this b to the t go away. I don't like cancellation. I won't use it because people misuse it. I go back to the rules. Divide both sides by b to the t. And then I can write this as b to the t over b to the t times b to the t dub equals 2 b to the t over b to the t, 1 times b to the t dub, b, it's a superscript, not a subscript, that's what happens when you get moving. You don't pay attention. And of course, I always, anytime I do something like this, I'm just pretending. So you won't feel bad if you do it, but I also correct it as you should. And if you believe that, well, okay, anyhow, 1 times b to the t dub equals 2. So, b to the t dub equals 2. How do you solve this equation? Well, you just solved a bunch of exponential equations by converting them to logarithmic equations. T dub is log to the base b of 2, which is log 2 divided by log b. So that's the doubling time. Now let's just be clear about something. What then is the doubling time of y equals a b to the t? Well, that says that a times t dub later is equal to ab to the t. Just as this did, of course, except you didn't have the a in there. What are you going to do about the a? Well, we have this. A little tedious writing all this out, but I want to really reinforce that we don't cancel. We work it out and show that it's really true. And if we don't do it on paper, we better do it in our heads and make sure we're right. Because it's awful easy to cross out things that shouldn't be crossed out. So anyhow, there it is. And very clearly, if we divide through by a, the a's go away, and we end up with this. And here are the details of why the a's go away. Not because you can cross things out. You know, people would cross out the b and dub here with the b and dub over here on a different part of the page if you let them. Now y'all are not going to do that. And very few people actually would. That's an exaggeration. But sometimes it looks that way to me. Okay, so this is the same as this. Or let's just say this is the same as this down here. So everything else follows just as it did up here. And we get T dub equals log of 2 of 2 over the log of b. Okay? So it's identical. This tells us that once you've figured out how long it takes the function to double, and once you have one point on the graph, you can construct all the rest of the graph. So I wanted to construct the graph of an exponential function, just a plain old b to the t exponential function, meaning the graph goes through the point 0, 1. That's automatic for any exponential function that hasn't been vertically stretched by a factor that we call a. And if I've got any other point out here, well, and I know, well, I don't even need that. If I know the doubling time, then I just draw a bunch of doubling times, and I go backwards into negative numbers. And I know that for this value of x, it's going to be twice as big as this, so I can double this, and I get this point. Then if I go over to here, I'm going to double this value, which will bring me up to here, and I'll get this point. And if I go over to here, it doubles again, which brings it all the way up to here. Well, that's kind of off my graph, but what the heck, I'll do it anyway, maybe up to here. So it's going to do this. That's going to level off, and over here, it's got to be half as much as it was after double. So that puts it about here. Here it's going to be half as much, puts it about here. And there we have a graph. Now this idea of doubling time is really important. You can imagine, for example, you have your compound interest. Okay, so if you're compounding your interest continuously, let's say, because that's what you really like, but it doesn't have to be continuous. Well, actually, I'm not going to do continuous. I'll do a discrete one first. Not discrete, but yeah, it's discrete. Okay, so compound interest. Let's say you've got P of t equals, oh, I'll always give you $1,000, shoot, just ask. $1,000 times 1.06 to the t, that would be 6% interest compounded annually, where t is in years. We could write out the same equation we did before. Then, remembering what we did before, at least in short term, we understand if we divide both sides by 1,000, we get 1,000 over 1,000 at each side, that's 1. And we're going to get this, which should be familiar if you understand what we did just a minute ago. So I'm not going to explain it. And we get this. At least, if we forget to write our 2, we get what I just wrote. But if we write our 2 in there, we get this. And then we divide by 1.06 to the t. Run through the details. At least do them in your head. Make sure you're doing the right thing. We get 1.06 to the t dub equals 2. Equals, so t dub equals, now if we formally do this, it's log base 1.06 of 2, but that's log of 2 over the log of 1.06, okay? And that's actually going to be kind of close to 12. There's this rule of 72 that I think you're going to see in your text, and it's handy if you're thinking through what you could expect from an investment. Of course, if I invest $1,000 today at 6%, I've got to also calculate in what I think the annual inflation rate is going to be to see what it's really going to be worth. But hopefully the economy beats the inflation rate, which is questionable these days. And the point is that this is 6% annual interest. If I divide the annual interest into 72, I get the number of years it's going to take to double, approximately. Okay, and for interest rates in the realistic interest, for low interest rates, The kind of interest rates that we typically get. 6% is a pretty high interest rate right now. If you get a safe investment at 6%, I'd take it. And we're going to advise you research it. So that's where I got the 12. I didn't do any fancy estimates over here. I just used the rule of 72 because I know it applies pretty well in this case. So that's, worth knowing. Okay, well, that means your money's going to double every 12 years. So 12 years from now, and what is this year? Is it 1976 or, no, it's 2020. Okay, means by 2032, when you're 12 years older than you are, you'll have $2,000. And hopefully that'll be worth more in 2032 than $1,000 is today. But you can't predict that. Population. Well, population growth models, unrestricted population, unrestricted, and I'll say continuous growth at 6% annually. Well, population could be expressed as a P. P of 0 is your population times 0, whatever that might be. Put any number in here you want. That would be P of 0 times e to the 0.06t. To double that, you would want P of 0 e to the t is how much you have at time t. If you want to double that and figure out when that occurs, you figure out what you got to add to t. In other words, what are you going to get when are you going to be, for what t dub are you going to be, is your amount doubled after t dub? Okay, again, like what I said before, here's double your population at time t. Here's your population t dub later at t plus t dub. Well, you do the arithmetic on this, and you again end up, the P of 0 divides out, you end up with this equals 2 times this. You get e to the 0.06t plus 0.06t dub equals 2e to the t, and it's e to the 0.06t. Okay, didn't write the 0.06 in before because I'm being careless. Okay, and then that's e to the 0.06t times e to the 0.06 t dub equals 2e to the 0.06 t. We divide through by the e to the 0.06 t, do the details, we get e to the 0.06 t dub equals 2, so that .06 t dub is log base e of 2, which is the natural log of 2 which is 0.69 something, pretty close to 0.7. So I'm going to say that's approximately 0.7. And we're talking about a population. If it's in the real world, using 0.69 or 0.7 isn't going to make a lot of difference because we've got a lot of uncertainty in how the conditions might evolve. So we're just doing an estimate of the doubling time anyway. So if it's just an estimate with a lot of uncertainty, it'd actually be safe to use 0.7. We don't need 14 decimal place answers. Estimating the population of this herd 30 years from now to the nearest molecule of creature, we don't need that. If we're anywhere close, we've made a good estimate. Okay, so anyhow, you get this so that T-dub is about 0.7 over 0.06. Now, remember what I said about the rule of 72, we divide 72 by the interest rate? Well, this is a lot like dividing 70 by 6, isn't it? Pretty close to 72 over 6, pretty close to 12. To the nearest year, that would be 12. Be 11 2/3. So the arithmetic, the algebra is practically identical for population. And there are other applications that you're going to see by the time you complete the assignments for next Tuesday. Okay.